everyone, and welcome to this online tutorials for the course of op-amp and linear ICs. So today's in this lecture we will be seeing about the topic of comparators. So first of all, what is a comparator? A comparator, as its name implies, compares a input signal of one input of an op amp with a known voltage called a reference voltage on the other input, and it in its simplest form we can say it has a open loop configuration with two analog inputs and one digital output. The digital output we see here mainly because the op amp is used in open loop configuration, and when used in open loop configuration it provides a saturation voltage, either a positive saturation voltage or a negative saturation voltage. So seeing the objectives of this particular topic here, that is about the comparator, we will be discussing the operation of basic comparator circuit, draw the input-output waveforms of the comparator circuit, and define a reference voltage as it relates to a comparator. So first of all, we will see what is a basic comparator. The op-amp in an open-loop configuration can be used as a basic comparator. When two inputs are applied to the open-loop configuration of an op-amp, then it compares the two inputs. Depending upon comparison, it provides a positive voltage, which is a saturation, positive saturation voltage, or a negative saturation voltage. A comparator is a circuit which compares a signal voltage applied at one input of the op amp with a known reference voltage at the other input. It produces either a high or a low output voltage depending on which input is higher. Since comparator has two voltage levels, it is not linearly proportional to the input voltage. There are two types of comparators. The first one is the non-inverting comparator, and the second one we call it as a inverting comparator. So we will be seeing the first part here, that is the non-inverting comparator. In this, the input is applied to the non-inverting terminal, and the inverting terminal is grounded. So grounded in the sense the reference voltage is considered to be 0. Seeing the operation of this particular circuit, when an sinusoidal input is applied to the non-inverting terminal, as we know, the sinusoidal input has two parts. One is a positive part and another one is a negative part. The circuit operation can be divided into two parts, positive as well as negative. When V in is greater than V reference, that is greater than 0, the non-inverting comparator, in the non-inverting comparator, if V in is greater than V reference, then output is plus V sat, what we can say. And if V in is lesser than V reference, that is 0, then we can say the output voltage is minus V sat. Since this is because the open loop gain AOL is very high, even for small input voltage V in, the op amp output saturates. Note that there is no feedback applied to the op amp, and it is operated in open loop conditions, because of which op amp is operating in saturating conditions. The input and output waveforms for a basic non-inverting comparators are seen in this particular slide here. So here we can see the input output waveforms. During positive half cycle we get a plus V saturation, and during negative half cycle we get a minus V saturation, mainly because this is a non-inverting configuration. Now moving further, the op amp differential voltage gain A naught L is very large. Hence very small input voltage applied, the output saturates. The saturation voltage levels are mentioned in the data sheet. Knowing the saturation voltage level and the differential gain, the minimum input required can be obtained from this particular expression. That is, we can calculate minimum input voltage as V sat divided by the differential voltage gain, or the open loop gain, what we call. The point at which the transfer characteristics is straight line is called a trip point, that we can see in the curve of v naught versus v in, which we call it as a transfer curve. And till that straight line we call it is linear. After that there is a trip point occurring. The trip point is the input voltage at which output voltage changes its state from low to high or high to low, so either of it parts. In basic comparator, the trip point is 0, as at V in is equal to 0, output changes its state. As this change over occurs at V in is equal to 0, the basic comparator can be used to detect occurrence of 0 in the input voltage. Hence, this circuit is also called as zero crossing detector. It is possible to change the trip point from 0 voltage to some other voltage, and this is achieved by some modifications in the basic comparator circuit. By application of the reference voltage at the inverting terminal rather than grounding it, the trip point can be moved. Seeing this particular circuit here. So instead of connecting the inverting terminal directly to ground, it is applied to a potential divider network from R1 and R2 to a supply voltage plus VCC. And there is a bypass capacitor is used, which eliminates all the AC components present in that DC components, the noise part in it. The reference voltage is derived as from the reference voltage is nothing but it is a voltage across the resistance R2, and it can be obtained as V reference is equal to VCC times R2 divided by R1 plus R2. Now seeing the operation of this circuit, if V in is less than V reference. Now we are comparing it with V reference. If V in is less than V reference, then output voltage V naught is minus V sat, that is a lower value. And now if V in is greater than V reference, then output voltage V naught will be plus V sat. The bypass capacitor is used to reduce the amount of power supply ripple and noise appearing at the inverting input terminal of the op amp. From the transfer characteristics, it can be observed that output changes its state at a positive trip point, and such a comparator is also called as a limit detector, since it detects the particular positive level of input beyond which output goes high. The trip point can be set anywhere between 0 and plus VCC. It is also possible to provide a negative trip point by providing a negative reference voltage. Seeing this particular circuit, instead of plus VCC, we have applied minus VEE, and we get V reference as minus VEE times R2 divided by R1 plus R2. In this case, now what happens? When V in is greater than V reference, when V in is greater than V reference, V naught is equal to plus V sat, that is a higher value, and when V in is lesser than V reference, V naught is equal to minus V sat. So this is also called negative reference. So these are the input and output waveforms for a positive trip point and a negative trip point. Everyone, and welcome to this online